In this video, we will be looking at the mode control panel of a modern airliner. We will look at the 737-800 version of the panel. Clearly there will be differences for various types of aircraft, such as the Airbus, but in essence the theory behind it will be the same. This is a picture of the mode control panel we will be discussing. There are various buttons and functions which we will discuss a little later in the video. But what is the mode control panel for? It is where the datums set by the pilot are entered. These datums are then fed to both the flight director system and the autopilot. It is worth noting that certain parts of the mode control panel are repeated on both sides. These are the course settings and the flight director switches. This allows the captain and first officer to have independent control of their course selector and flight director. We should firstly explain the flight director system, as this may give some clarity of the function of the mode control panel. Again, aircraft vary with their presentation, but in this example, we will be looking at the standard, crosshairs, version. The flight director will appear in the pilot's flying display unit, specifically in the artificial horizon section, which is called the attitude indicator. The crosshairs flight director is designed so that when the pilot is flying to the datum set in the mode control panel, the vertical and horizontal magenta lines are both horizontally and vertically centered, as shown. The two magenta lines should cross in the small black box, as shown. In this example, the pilot is maintaining exactly what is set in the mode control panel. In other words, 37,000 feet, 220 knots, and the desired heading are entered into the panel. As the flight directors are central, and cross inside the little black box, the pilot is flying exactly as required. In this example, changes in both heading and altitude have been changed in the mode control panel. Therefore, the flight directors have demanded a roll to the right, and a pitch-up attitude, to allow the aircraft to fly to the new datum. In this example, the pilot must add more right roll, and more pitch-up, to center the flight directors. We shall now explain the various function of the mode control panel, and what can be entered. Starting at the very left, we see the course setting. Using the rotary knob, we can set a course setting from 0 to 360 degrees. We use the course selector to enter the approach track of the ILS system we may be using. Or, as per this example on the navigational display, display a line to or from a beacon for reference. The course setting will determine the track presented to, or from, the beacon. Moving across, we come to the flight director switch. This will turn the associated flight director off. In this case, the captain's flight director. If turned off, the pilot will not have any flight director guidance, and the crosshairs will disappear. This means the pilot will have to fly the aircraft on pure instrument flying, which we call raw data. Above the flight director switch is a green light, labeled MA. When lit, this will indicate whether the mode control panel uses the captain's, or first officer's navigation system settings, as reference. In this instance, the master is set to the captain's side, so all navigational information is taken from the captain's navigation systems. Next to that, we have the autothrottle arming switch. This activates or deactivates the autothrottle system. The switch is spring-loaded, so can either be deactivated by pushing the switch down, or by pressing a button on the side of the thrust lever. Now we move on to the speed control area of the panel. As you can see, there are a number of selectors and functions in this area. The N1 button is a function of the autothrottle, and is available once the autothrottle is engaged. When pressed, it instructs the autothrottle to increase the thrust to a predetermined datum, such as climb power. The speed window is where the desired speed is selected. The speed is changed using the rotary knob. Whatever is selected in the speed window will appear on the pilot's flying display, both as a speed bug and as a numerical number above the speed display. The speed window will display both knots and Mach number. Usually the changeover between the two is automatically done in the climb, or descent, at a suitable altitude. However, it can also be changed over manually, using the changeover button. There are two modes of speed control. The first is activated using the speed button. This button is usually engaged when the aircraft is level, so the speed will be controlled by the autothrottle. It can be engaged manually, or will be automatically engaged when the aircraft levels off at the desired altitude. The second is the level change button. The level change button will initiate a climb or descent, depending on what level the aircraft is at, compared to what is set in the altitude window. For example, if the aircraft is at 20,000 feet, and the altitude window is set to 30,000 feet, the level change button will initiate a climb. For the climb, it will engage the N1 button, to set climb power, and the speed set in the speed window will be maintained by raising or lowering the pitch attitude. If the altitude window is set at a lower value, say, 10,000 feet, the level change button will initiate a descent. It will command the thrust levers to close, and the speed will again be controlled by pitch angle. Note: the speed and level change button cannot be engaged at the same time. Likewise, the speed and N1 button cannot be engaged at the same time either. The VNAV button takes the flight control to a higher level. Once selected, the VNAV system will take control of both the speed, climb and descent profiles, and altitude control. The VNAV system will take its data from the flight management computer. The data is controlled by the Multipurpose Control and Display Unit, or MCDU for short. This is usually situated in the center pedestal. We will not go into any great detail here. However, for the VNAV system we can enter fixed altitudes and speeds into the route. In this example, we have set specific altitudes into the route that we wish the aircraft to fly to. You can see from the display that 6,000 feet has been entered by the pilot into the MCDU. This means that the pilot wants the aircraft to be at 6,000 feet by rebas. The VNAV system will now compute the profiles to reach 6,000 feet by rebas, and will compute the climb point accordingly. The entered altitude is in larger font than the other levels, to indicate that this has been entered as a restriction. The smaller values denotes what the computer thinks the aircraft will be at that point. In this example, the 7,000 feet could indicate there is another level restriction later in the route. Providing the altitude window is set correctly, the VNAV will fly to those altitudes, and will calculate the correct climb or descent profile, plus any speed adjustments, to get the aircraft to the desired altitude and speed. The pilot can also enter fixed speeds. Although these are not present in this example, any entered speeds would appear as larger font as well. The VNAV system would then fly the aircraft at that speed by that point. In the absence of any entered values, the VNAV will fly a height and speed profile, as entered in the initial setup. With the VNAV engaged, the speed window will now go blank. This is because the VNAV is now in charge of the speed. However, the speed bug will still appear on the speed display, to indicate what speed the VNAV has commanded. However, if for any reason the pilot wishes to regain speed control, but is happy for VNAV to continue to look after the vertical profiles, the pilot will press the Speed Intervene button. This will reopen the speed window, and the pilot can control the speed as before. If the pilot then wishes to revert back to full VNAV function, the Speed Intervene button is pressed again. The VNAV has a lot of authority over height and speed profiles. Providing the flight management computer has been properly programmed, it reduces the amount of speed and profile changes having to be made manually. Now we move along to the lateral control. These include heading and navigational control of the aircraft. The heading system is a basic system that makes the aircraft follow a basic heading. This is used when air traffic control give the pilot a heading to follow. The heading system is active when the heading select button is pressed. The aircraft will then follow the heading displayed in the heading window. The heading can be changed using the inner rotary knob. The heading is displayed as a heading bug on both the pilot's flying display and the navigational display. The outer rotary knob tells the flight director system what maximum angle of bank should be used whilst in heading mode. Usually we use 25 degrees, but that can be adjusted for performance or procedural reasons. For example, on one engine at slow speeds, the maximum angle of bank will be set to 15 degrees. The scale is repeated both sides so that both pilots can clearly see it. The VOR lock button is selected for two functions. The first is to track to, or from, a VOR beacon. The course window is set to enter the track to, or from, the beacon is required. This was discussed earlier in this video. The second function is to follow the localizer, or horizontal beam from an instrument landing system. The localizer course will also be entered into the course window. The function will depend on what facility is entered into the navigation system. The next function is the approach mode, which is activated using the app button. This will engage both the localizer and glide slope beams, or horizontal and vertical tracks, of an instrument landing system. Again, the approach course is set into the course window. The approach mode allows for a fully automatic approach to a runway, and will also allow an automatic landing, if the aircraft is landing in very poor visibility. The last function in this section is the LNAV mode, and is activated using the LNAV button. Similar to the VNAV system, the LNAV system takes its data from the route that is entered into the MCDU. This route will be displayed in the navigation display as a magenta line, with each waypoint displayed as well. LNAV will steer the aircraft to follow the track as displayed, steering a heading to take into account the wind. The next section is the altitude control section. This includes the altitude selection, and vertical speed mode. The required altitude is selected in the altitude window. In this example, 37,000 feet is the required altitude. If the aircraft is not yet at that altitude, one of the climb modes, such as level change, can be engaged. This will make the aircraft climb or descend, to achieve the desired level. The rotary knob is used to change the value in the altitude window. Each click will change the altitude by 100 feet intervals. The set altitude is then displayed as an altitude bug on the pilot's flying display. Note: whatever is set in the altitude display window will be the overriding limit. For example, if VNAV wishes to climb the aircraft to 39,000 feet, but the altitude window is set to 37,000 feet, the aircraft will level off at 37,000 feet, and will not climb again unless the altitude window is changed. The Alt-Hold button is pressed if the pilot wishes the aircraft to level off whilst in a climb or descent. For example, if the Alt-Hold button is pressed in the climb passing 24,000 feet, the aircraft will stop the climb, and adjust the aircraft level to 24,000 feet. Further corrections can then be made. Pressing the button does not change the value in the altitude window. The vertical speed system allows the pilot to fine-tune rates of climb and descent. An example would be during a non-precision approach to an airfield, where there is no vertical beacon guidance. Another example is to reduce the rate of climb in busy air traffic areas, where high rates of climb and descent are not advisable. Providing the aircraft is not at the altitude set in the altitude window, the vertical speed system can be activated by pressing the VS button. This will open the vertical speed window, which will display the rate of climb or descent at the time of pressing. Rates of descent are displayed with a minus sign on the left. The rate of climb or descent can then be adjusted using the wheel shown. Whatever is selected in the vertical speed window is then presented as a magenta bug on the rate of climb and descent window on the pilot's flying display. In this example though, the aircraft has just leveled off, so the bug will disappear. Once leveled off, the vertical speed window closes, and the vertical speed system cannot be reactivated until the altitude window has been changed. Finally, in this section, we will look at the altitude intervene button. If you recall from earlier in the video, the aircraft will level off at 37,000 feet in this example, even though the VNAV system wants to climb to 39,000 feet. If we are then cleared to 39,000 feet, we then reset the altitude window to 39,000 feet. Nothing will happen at that point until we do something else. We could press level change to start the climb, but as we are in VNAV mode, and want to remain in that mode, pressing the altitude intervene button will commence the climb in VNAV mode. The final section of the mode control panel is the Autopilot Engagement section. This aircraft has two autopilots, A and B systems. Autopilot A takes data from the captain's systems, whereas Autopilot B takes data from the first officer's systems. Usually, only one autopilot is engaged at any one time, unless the aircraft is doing a full auto-land approach. In that scenario, both will be engaged. To engage an autopilot, either the Command A or Command B button is pressed. This will engage the associated autopilot. To swap autopilots, just press the other button. To disengage the autopilot, press either the Active Command button, or more usually, press the Autopilot Disconnect button on the control column. Either method will sound a short warning tone to let you know the autopilot has now disengaged. If for some reason the disconnect does not work, the autopilot disengage lever can be pushed down, which will remove power from both autopilots, forcing it to disengage. To restore power, the disengage lever must be pushed back up again. Once engaged, the autopilot will now fly the datums set in the mode control panel, as if it is flying to the flight director. However, the autopilot can be used to hold a pitch and roll attitude. To do this, the pilot engages the course wheel system. By pressing the associated course wheel button, the autopilot will hold the pitch and roll value at the time. The pilot can change those values by using the control column to change pitch and roll. The course wheel system will then hold the new datum. To come out of course wheel mode, either the autopilot can be disconnected, or a lateral and vertical mode be selected, such as LNAV and VNAV. This concludes this video on the mode control panel. The video only gave a basic description of the panel, and you may appreciate there is a lot more to it. However, an important lesson must be learned from all this. The flight director and autopilot system will only fly to the data the pilot enters. It cannot think for itself, nor will it get the pilot out of trouble if incorrect data has been entered. It will, basically, do as it is told, and will happily fly you into a hill if you let it. That's it from us. See you next time.